Good afternoon, friends, and welcome again to one more session of Physics Class 12. Today, we are discussing another important topic, that is electrostatics potential and Gauss's theorem. This is a very important chapter of electrostatics. As you all know, that this is the third chapter of the electrostatics part. So, initially we have done Coulomb's law, then we have done electric field, and now this is the third part of the electrostatics chapter, Physics Class 12, which is electrostatics potential and Gauss's theorem. So let's get started with this, and before we get started, I want to just request you, please visit to my personal mobile number. If you have any doubt, any confusion regarding any part of the explanation, you can contact me directly in this number. You are watching Parijat sir classes, so please like, share and subscribe my channel so that I get motivated to make more and more videos for your upcoming physics classes. Okay, so let's get started. And as you all know, that along with physics, I am already uploading the maths classes of class 12 mathematics, so you can also watch the videos of the maths class 12 chapters. So let's get started with electrostatic potential. Okay, so first of all, what is electrostatic potential? What is electrostatic potential? So, as you can watch here, whenever a charge, as you can see here, whenever a charge Q, this is a charge Q, is moved from point A to point B, I am moving this charge from point A to point B in an electric field due to charge Q. Please watch, this is the charge Q, so it will have electric field outwards. It will have electric fields like this. It will have electric field like this. Okay, so when you are moving this charge in the electric field of this charge, then you have to work against the repulsive force between the charges. Okay, so there will be a repulsive force and you have to work. There is a repulsive force and you have to work against the repulsive force, and this work is stored as potential energy in this charge. The work done by you to move against the electric field is stored as a potential energy in the charge. Okay, so let's see, if we are moving from A to B against the electric field, so how much was, since we are moving from against the electric field, so it is a minus, so A to B, and work done is force, electric force into displacement. Okay, so this is the expression for the work done, which is stored as a potential energy in the charge. Okay, so this work done depends only on the initial and the final positions and not on the followed path. You can reach from A to B along this path, or along this path, or direct, or along this path, or along this path. Okay, you can bring the charge plus Q from any path from A to B. So work done will not depend on the path. Please note this, work done will not, the work done depends only on the initial and final positions and not on the path followed. Okay, very important point. Thus, electrostatic potential energy of the charge Q in an electrostatic field due to any charge is the work done by the electric force. So what is this? So what is the electrostatics potential energy? It is the work done. So electrostatic potential energy is the work done to bring a charge from one point to another against the electric field of any other charge. Okay, and please remember, the work which will be done, this will be without any acceleration of the charge. Please mind it here, without any acceleration of the charge. Please watch here, you cannot have any acceleration when you are moving the charge from any point to any other point. Clear? Very important point. Next, what we will see is electrostatic potential difference. Now we have seen the potential energy. Now we will see the potential difference. So what is it? Electrostatic potential difference between any 2 points A and B. So this is the point B and this is the point A. So what is the electrostatic potential difference? So watch it. It is the work done in carrying a unit positive charge without acceleration from A to B along any path. So from any path you move, if you are taking this charge along any path without acceleration, and if this charge is a unit positive charge, then potential difference is the work done from A to B. This is the potential differences definition. Okay, so work done is independent of the path chosen from A to B. So from any path you can come from A to B, the work done will be same. Clear? So let's see. So what is the potential difference? It is the work done to carry a unit positive charge. Unit positive charge. It will be the work done to carry a unit positive charge. Okay. So this is the work done's dimensional formula is, we all know that, and charge is current into time, we know this. So this is the dimensional formula of the potential difference. Now watch, if the potential difference is 1 volt, W is 1 joules and Q is 1 coulomb. So what is 1 volt? It is when 1 joule of work is done to carry a unit positive charge from A to B. From A to B, if I carry unit positive charge, okay, and if I do 1 joule of work, then 1 volt will be 1 joule per unit charge. This is the thing. So SI unit is joules per coulomb or Newton meter per coulomb. Let's move on to the next. So what is electrostatic potential? What is electrostatic potential? So let's see what is it. Electrostatic potential at any point in an electrostatic field is the minimum work done in carrying a unit positive charge from infinity to that point. Okay, so what is the potential here? What is the potential here? It is how much work I will do to carry one positive charge from infinity to that point. That is the electrostatic potential. From infinity to that point, how much work should I do to bring the unit positive charge from infinity to that point A is called the electrostatic potential. Next is electrostatic forces are conserved. What does it mean? Electrostatic forces are conserved. Okay. What does it mean? It means work done in moving a unit positive charge from A to B along L will be given as how much? Suppose I take a unit positive charge from A to B along L. So I have to write down VAB, work done from A to B in carrying the unit positive charge is VB minus VA. Similarly, work done if I move it along A to B, now B to A along L, B to A along L, I have to write WBA by Q0 is VA minus VB. Now if I add these two, total work done, you will see that these all are cancelling out. These all are cancelling out and we have total work done is 0. And since total work done is 0, so we can tell that the total electrostatic forces will be conserved. Work done, total work done in a closed path. When you go from here to here, you do some work done. When you go from here to here, you do some work done. So when you reach back again A, then the total work done is 0. Okay. Now work done, as you can see, is force into displacement. And what is force? Force equal to Q into E. If it is a unit positive charge, F is equal to E. So E dot dl, this is the displacement. E dot dl is the total work done in around a whole cycle, complete cycle. So total work done is 0. E dot dl is 0. That means electrostatic forces are conserved. This is the explanation of this. If they show that electrostatic forces are conserved, this is the explanation of this. Since no work is done in carrying unit positive charge in an electric field over a closed path, so electrostatic forces are conserved. So if you want to show electrostatic forces are conserved, you have to show that total work done in a closed cycle will be 0. Next, we are going to study electrostatic potential due to point charge. Now, what is the electrostatic potential due to a point charge? So let's see that. This is the point charge plus Q. I want to find out what is the electrostatic potential at a point P. Okay. So first of all, let us see that what is the electric field at A due to the plus Q. What is the electric field at A at a distance of x? It will be given like this. And because it's a positive charge, so along OA, electric field at A, distance x. What is the electric field at A? This is the electric field at A. Now, if I take a unit positive charge and move from A to B, from A to B, I want to move. So what is the work done? What is the work done? E dot dx. See, this is the distance given, dx. Dx is the distance. Okay. And since I have taken a unit positive charge, F is equal to E into Q. If this is 1, so F is equal to E. So that means this is the total work, this is the work done if I move a distance dx. And now please watch, the direction of E is like this and dx is like this. That means there is a 180 degree between them. So E dx cos 180, which is minus E dx. This is the work done in taking the unit positive charge from A to B. From A to B. Okay. So the total work done to carry the unit positive charge from infinity to P. Infinity to P. So where is P? Here is P. Here is P. So I want to find out. So please watch here. This is the point P. This is the point P and I am coming from infinity. From infinity, the work done to move from A to B, distance dx, is given by this. So what is the work done in moving from infinity to R? This is the work done. So this is the E. This is the E dx. Q by 4 pi epsilon O is the constant, goes out. 1 by x square integration is minus 1 by x. 1 I will put R, then I will put infinity. So it comes out, this is 0. So it comes out to be minus minus plus. This is the work done to carry unit positive charge from infinity to the point R. So what is potential? Potential is work done by charge. So this is the work done by the unit positive charge. So this is the potential at a distance R due to the unit positive charge. This is the potential due to the unit positive charge at a, so please remember, okay, if there is a positive charge at a distance R, here the potential will be Q by 4 pi epsilon O R. So this is the relation for the potential due to a charge Q at a distance R. Now watch here, if R is 0, potential is infinite. If R is infinity, potential is 0. That means at infinite distance from Q, the potential is 0. If Q is positive, V is positive. If Q is negative, V is negative. So this is the relation for the potential. This is the relation for the electrostatic force between two charges. This is the relation for the electric field. So that means, see, the electric field and the electric forces, they vary as 1 by R square, and electric potential varies as 1 by R. Okay, so electric field and electric force vary more fast, they change more fast. Next, electrostatic potential due to a group of charges. So see here, suppose these are the collection of the charges, as you can watch here. Here is a point, this is a charge Q1, Q2, and here Q3, Q4, Q5. The distances are given. So what is the electrostatic potential at this point? It will be the summation of all the charge by the distance, summation of the charges. That means it will be 1 by 4 pi epsilon O. It will be Q1 by R1 plus Q2 by R2. In this way it will continue. Electrostatic potential at a point due to an electric dipole. Now watch this, very, very important. I want to find out what is the potential. This is a dipole, see, minus, equal and opposite charge separated by a distance 2a. I want to find out what is the potential at this point. What is the potential due to the dipole? So let from the center the distance be R, and this is R1 and this is R2, and let the direction displacement make angle theta. So the electric dipole moment is from the negative to the positive, as you can see. Now for the plus Q charge at a distance of R2, what is the potential? This is the potential for the plus Q charge at a distance of R2, and for the minus Q charge the potential is this. Okay, so what is the net potential? We will add these two, this. Now watch one thing. This is the thing which you have to remember, that is R1 square is equal to R square plus, this is A and this is A. So R1 square is equal to R square plus A square plus 2AR cos theta. Theta. Please remember this. Please remember this thing, that if this is A and this is B, theta C. So please remember, C square is equal to A square plus B square plus 2AB cos theta. Please remember this. So R1 square will be this and R2 square will be, for R2 square I will take this angle, 180 minus cos theta. 180 minus cos theta is minus cos theta. So this is R2 square, this is R1 square. So please note this, because this is a very, very important thing, that R1 square is this. You have to remember this relation, and R2 square is this. This is R2 square. Now we will put these values in the derivation. So r1 square is equal to, taking r square common, so it becomes this. And if a is very less than r, then we can easily neglect this part. So this is r1 square. So what is r1 to the power half? And using binomial theorem, this half will come in front. So you can see this half will come in front. So this is the 1 by r1. This is r1. So 1 by r1 is to the power minus half. Okay. So when this, using binomial, when this comes in front, so here it will come. So minus half. Okay. So 1 by r1 will be 1 by r 1 minus half into 2a by r cos theta. So this 2 and 2 cuts, so it's a by r. So this is what we have got it. Similarly, 1 by r2 will be this. So putting here the values of, this is 1 by r1, r2, this is 1 by r1. So now after cancellations we get this. So now we can arrange it like this. Q into 2a is called the dipole moment, cos theta 4 pi r square epsilon o r square. So this is the potential. Please watch here. This is the potential due to a dipole. This is the potential due to a dipole. Okay, this is the potential due to a dipole. So very important topic. Next, case 1. On the axis, if I want to find out what is the potential on the axis, so please watch, on the axis means r will be 0. This is the axis. Axis is AB. So if I want to find out on the axis, I will take theta as 0 degree. Okay, or pi degree, pi if it is oppositely directed. So the value of P will become this. And on the equatorial plane, theta is 90 degree and V will come 0. So please remember, if you are taking a dipole along the equatorial plane, potential everywhere will be 0. And if this is a dipole, and you want to find out on the axis, along the axis, so this is that formula, plus minus P by 4 pi epsilon o r square. This is the potential. Clear? So you have to keep this in mind, P cos theta by 4 pi epsilon o r square. Next we will find out so let's see what are the some important points, some very important points about potentials concepts. Potential due to a point charge varies inversely as the distance, as we all know that, we found out. But potential due to a dipole falls more rapidly. Dipole is proportional to 1 by r square, as you have seen, and due to a point charge it is proportional to 1 by r. So dipole's potential will fall very fast. Second, potential due to a dipole depends on the angle between the dipole and the position vector. Definitely V is proportional to cos theta. Okay. Potential due to a dipole is symmetrical about the dipole. That is, same potential exists around the dipole. So if this is the dipole, around any point, if I want to find the potential, its potential will remain same in this region. Its potential around the dipole will be symmetrical. So since everywhere the potential will be same, here the potential will be same, here the potential is same, here the potential is same, here potential is same. So if I want to move around that symmetrical line, no work will be done. No work will be done along, if I move along in that symmetrical line. No work will be done if I take a charge like this and move around the dipole. No work will be done to move the dipole like this. Clear? Okay. Next, equipotential surfaces. What are equipotential surfaces? As you all know, equi means equal. A surface at which every point potential is same. That means here the potential, here the potential, here the potential, here the potential, here the potential. Everywhere the potential is same. So there is no difference in the potential. No difference in the potential. So if there is no difference, no work will be done in moving the charge over the equipotential surface. Very important. We will not do any work if I move along the equipotential surface. Second, electric field is always normal to the equipotential surface. So please watch here. We know work done is line integral of E dot dl. Okay. So E dl cos theta equal to 0. E dl cos theta equal to 0. Right. Now, what we will do is that if E, and how can we make it 0? If theta is 90 degree. If theta is 90 degree, then only E will be perpendicular to dl. That means if this is a surface, electric field is always perpendicular to the surface. Always electric field will be perpendicular to the surface. Okay, please note that. Electric field is always on the equipotential surface, electric field is always normal. Equipotential surfaces of a single charge are concentric surface. So this is the diagram for the equipotential surface of a point charge. Point charge, this is the electric fields around the point charge for equipotential surfaces. They are concentric, symmetrical also. So let's see next. So here, now we will study the relation between electric field and electric potential. We will study the relation between electric field and electric potential. So please watch. Electric potential decrease, they are very important, in the direction of the electric field. If this is the electric field's direction, potential will decrease. Suppose here is 10 volt, here it will become 8 volt. That means if you go along the direction of the electric field, your electric potential will always decrease. Very important. The negative sign shows that the direction of the electric field is in the direction of decreasing potential. Very important line here. Decreasing potential. That means electric field will always go in the direction of decreasing potential. In the region of strong electric fields, equipotential surfaces are close and vice versa. That means if you are having a strong electric field, so this will be the potential lines, very very close, strong electric field, and if there's a weak electric field, the lines will be, potential lines will be separated far. Okay. Electric potential is a scalar quantity, but electric field is a vector quantity. Please remember, these are the different points about the electric field and potential. Next, electrostatic potential energy of system of charges. So if there are many charges, so what will be the potential due to the system of the charges? So first watch here, this is Q1. So what is the potential? What is the potential at this point due to Q1, which will be at a distance of R? Suppose this is R. So what is the potential here at Q? This. And what is the potential? So the potential at Q, as you can know, one minute friends. Okay, so the potential at Q here, the potential will be what? Q1 by 4 pi epsilon O R. And what is the potential at infinity? It will be 0. 0. So what is the potential difference between these two? It will be this only. Okay. So what is the work done to bring the charge Q2 from infinity to that point Q? So this is the potential into the charge is the work done, and that is the energy stored. That is the potential energy. That is the potential. So first of all, due to the charge Q1, find out what is the potential here. The potential at infinity is 0. So what is the potential difference? This only. So potential, we know that W is equal to the potential difference into the charge which you are bringing. So this is the potential difference into the charge, and this is the work done, and we know work done is the potential energy stored in the system of the charges. So due to the two charges, so due to the system of two charges, the potential energy is this one. Very important. And please note these relations. 1 electron volt is 10 to the power 1.6 10 to the power minus 19 joules. 1 milli electron volt is 1.6 10 to the power minus 22 joules. 1 mega electron volt 1.6 10 to the power minus 13 joules, and 1 giga electron volt is 1.6 10 to the power minus 10 joules. You have to note these values. Next, let's see. Now we are going to study what is electric flux. Flux. So please watch here. Flux. Electric flux over an area in an electric field represents the total number of electric field lines crossing the area. For example, if this is the electric field, if this is the electric field of any charge, okay, electric field, suppose I put here a surface, I put here a surface of area 1 meter square. So how many lines will pass through this area? How many lines will pass, electric field lines will pass through this area? That is called the flux. That is called the flux. Okay. So flux is E dot ds or E ds cos theta, and please watch here. Suppose you have placed the surface at an angle whose normal, the surface, this is the surface is normal, perpendicular to the surface is this, and it makes an angle theta with the electric field. So what we can write? Flux will be E dot ds. So E ds cos theta. Clear? So as you can see from here, if flux is E ds cos theta. Now if this theta is 0 degree, that means the normal is in the direction of the electric field. If the theta, so this is the normal of the surface and this is the electric field, so they are in the same direction, so theta equal to 0 degree. But if this is the electric field and you are placing the surface like this, so how will be the normal? The normal is actually like this, and this is the electric field, so the angle is 90 degree. So when this angle is 90 degree, here the flux will be taken as EDS, and here the flux will be taken as 0. Clear? So in this case, as you can see, flux is given as phi is equal to, for a closed surface, it is line integral of E dot ds, which is E ds cos theta. Theta is the angle between the normal and the direction of the electric field. Normal of the surface and the direction of the electric field. So electric flux is a scalar quantity. If theta is greater than 90, phi is negative. Okay, so please remember this. That means electric flux will go into the surface. If phi is less than 90, theta is less than 90, phi is positive, it will go out of the surface. And for this, the electric field lines will go into the surface. Okay, and if it is 90 degree, the phi is 0. So this is the dimensional formula of the electric flux, which is Newton. SI unit is Newton meter square per coulomb. Please keep remembering this. Next, very important point is Gauss's theorem. Very important point is the Gauss's theorem. So let's see what is Gauss's theorem. Total electric flux over any closed surface S is 1 by epsilon O times the charge contained inside the S. Suppose this is a surface S and here is a charge Q. So they are telling what electric flux will come out from this surface. What electric flux will come out from this surface will be Q by epsilon O. This is the total flux which will come out of the closed surface if there is a charge inside it. So please remember it. This is the Gauss's theorem. So E dot ds will be Q by epsilon O if it is in vacuum. If it's in vacuum. If it's in any other medium, Q by epsilon O epsilon R. Please remember this. So this is the Gauss's theorem. Next, proof of Gauss's theorem, which is again a very important topic. Proof of Gauss's theorem is important topic. So what is that? Let's see. According to Coulomb's law, electric field intensity at P on the surface. So see, suppose this is a surface, there is a positive charge and it is of radius R. So what is the electric field at P? What is the electric field at P? It will be definitely radially outwards. because this is a positive charge. So at a distance of r, what is the electric field? This is the electric field. Okay. Now let us consider a small element of area ds. This is the ds from where electric field will pass. I want to find out what is the flux through this. So it will be d phi will be E dot ds, which is E ds cos 0 y, because the surface is normal and the electric field are in the same direction. So theta is 0 degree. So d phi equal to E ds. So through the total surface, total flux over the entire surface will be line integral. Total flux through the entire surface will be line integral of this, and E is q by 4 pi epsilon o ds. So from here q by 4 pi epsilon o r square, r constant, comes out. Line integral of ds is 4 pi r square. So this gives you phi equal to q by epsilon o in vacuum. And in any other medium, if there was something inside this of relative permeability ER, then this would have been the flux. This would have been the flux. So this is the proof of the Gauss's theorem, that through a closed surface carrying a charge q, the flux coming out will be q by epsilon o. Now if q equal to 0 phi, that means if there is no charge inside the surface, if there is no charge, there is no flux. Or if the sum of the charges is 0, suppose inside it there is a plus 1 coulomb, there is a minus 1 coulomb, there is a plus 2 coulomb, there is a minus 2 coulomb. So although there are charges, but the sum of the charges is 0, and again the flux will be 0. So there will be no flux coming out if there is no charge inside the closed surface, or sum of the charges is 0. Next, deduction of Coulomb's law from the Gauss's theorem. Very important. Deduction of Coulomb's law from Gauss's theorem. So how can we get Coulomb's law from Gauss's theorem? So let's see. So again, imagine there is a sphere having a plus q charge at the center at a radius is r. So we all know, according to Gauss's theorem, the total flux coming out will be q by epsilon o. So E line integral ds will be q by epsilon o, and total area of the sphere will be 4 pi r square. So this is q. This is the value. This is the formula for the electric field coming out due to the positive charge q. The electric field coming out is this value. Now if I put a point charge q0 at a distance r on the surface, means if on the, so electric field coming out is like this. This is the electric field coming out. So if I put a charge of q0 here, so what is the force? Force is q0 into E, which is this, and this is only Coulomb's law. This is only Coulomb's law. So see how from the Gauss's theorem we got the Coulomb's law. That means Coulomb's law was established, so Gauss's theorem also got the establishment. Yes, Gauss's theorem is also correct. Next, see, electric field due to infinitely long straight charged wire. So please watch here. This is a wire. This is a wire, and suppose at a distance of r, we imagine there is a cylinder. This is the charged wire. This is the charged wire having positive charge. Suppose we take a length L of the wire, and at a distance of r, we imagine there is a cylinder around the wire. We imagine it. So what is the direction of the electric field? It will be positive, so out of the surface. Okay. So the total flux coming out will be line integral of the whole surface. That means E ds cos 0. So here this is the curved surface. So what is the direction, what is the angle between the electric field and the normal to the surface? It is 0 degree. So that is why we write, instead of E dot ds, we write E ds cos 0, which is E ds. E comes out, ds, total surface 2 pi r l. What is the curved surface? This is the curved surface. This is the curved surface of the cylinder, 2 pi r l. So this is the flux we calculated. But Gauss told that the total flux coming out will be Q by epsilon O. So we could equal these two. We found Q. Now what is Q? Q is the total charge, and we took let charge per unit length. Let the charge per unit length, charge coulomb per meter, be lambda. So therefore the total charge will be lambda into L. So putting here Q equal to lambda L, we get this. So L and L will cut. So this is the formula for the total flux due to the long infinitely straight wire. Long infinitely straight wire. This is the total flux coming out. So from here we can see electric field is inversely proportional to the R. We know that electric field here, this is the flux coming out. Okay, 1 minute. So sorry, this is the electric field. This is printed wrong. This is the electric field. Sorry. Please note here, this is the electric field due to a straight long infinite wire. So it is inversely proportional to the R. Now if lambda is 0, that means if the wire is charged positive, electric field is radially outwards, and if lambda is negative, that means you have charged negatively on the wire, so electric field is radially inwards. Radially inwards. Next, electric field due to uniformly charged shell. Electric field due to a uniformly charged shell. So see, this is a hollow shell of radius r. So I want to find out outside the shell what will be. This is a charged, suppose this is a uniformly charged shell, so this is charged of radius r. Okay, so I want to find out what is the electric field at a distance of r from the center. I want to find out what is the outside the shell at a distance r from the center. That means from here to outside, what is at a distance r, what is the electric field? So according to Gauss's theorem, the total flux coming out will be line integral of E dot ds, which is Q by epsilon O, because these are all charged. These are all charged. Total charge Q by epsilon O. Now E dot ds, that means E ds cos 0 degree, because electric field and normal to the surface are in the same direction. So this was the flux, and total flux is Q by epsilon O. So from here we write down E line integral ds Q by epsilon O, and total surface area is 4 pi r square. So this is the electric field due to a uniformly charged shell. Outside the shell, how much will be the electric field? Now if it is on the surface, your R is replaced by R and we get this is the electric field at the surface. Instead of R, we have replaced it by R square. Okay. Now let sigma be the charge per unit area. We have taken a shell. Let sigma be the charge per unit area. So for the whole area, what is the charge? This is the whole area's charge. Total surface area is 4 pi r square. Sigma is the charge per unit area. So the total charge on the shell will be this. So now let us, instead of Q, let us put this. So this is the electric field due to a spherically charged shell which is outside the shell. Okay, so watch here. At a distance which is r less than r, as you can watch here, this is the electric field, 0. Why? Because it is a shell and total charge is concentrated on the surface. That means there is no charge inside. Inside charge is 0, so electric field is also 0. So that means still a region of R, there is no electric field. And at the surface, when R is equal to R, this is the electric field. This is the electric field on the surface here of the spherical conductor. This is the electric field on the surface of the spherical conductor. Okay. And outside the shell is this formula. So we can see that up till 0 to R there is no electric field. At R suddenly it becomes maximum. And when R is greater, this is R greater than R, electric field will show inversely proportional to 1 by R square. It will decrease very fast. This diagram is also very important. Next, inside the shell at R less than R, Q is 0, so electric field is 0. Already we have done this. So friends, next, electric field, you want to find out the electric field due to a uniformly charged non-conducting solid sphere. Non-conducting solid sphere. Electric field due to a non-conducting solid sphere. So let's see. This is a solid sphere of radius r. Let sigma be the charge per unit volume. That means for unit volume, the charge is sigma. So radius is r. Now we imagine a small sphere of radius r. This is the radius r. So we know the flux coming out will be line integral of E dot ds. So E ds cos 0, because see, electric field and surface normal are in the same direction. So theta will be 0 degree. So E ds line integral, and ds will be what? ds is 4 pi epsilon o r square. This is E ds, this is E ds, this is the flux. But Gauss told the flux should be the charge enclosed within that sphere. So let the charge be q dash. Gauss told this. It should be the charge within that. Suppose charge within this is q dash. So it will be, flux will be q dash by epsilon o, and it is E line integral of ds. Now ds is the surface area of the sphere, inner sphere, 4 pi r square, q dash by this. So this is the electric field And now Q dash. What is Q dash? We know sigma is the charge per unit volume. So what is the volume of this inner sphere? 4 by 3 pi r cube. So that is the total charge. So let us put it here. Q dash. So after katakuti we get this. So this shows that electric field is directly proportional to the distance from the center. Electric field is directly proportional to the distance from the center. So at r equal to, so when r is 0, that means at the center of the solid sphere. So if r is 0, as you can see in this formula, if r is 0, E is 0. If r is equal to the radius of the bigger sphere, this is the electric field maximum. And outside, this conductor behaves as a single charge. So electric field will fall like this. So there are three sections. At r equal to 0, E is 0. And as r rises, as r increases to maximum value, the E becomes maximum. Outside, E is inversely proportional to 1 by r square. So these graphs are very, very important graphs. You have to note them down. You have to practice them along with the concept. Next, let's see. Electric field due to a thin infinite plane sheet of charge. Very important topic. Very, very important topic. This is a thin sheet. As you can see, this is a thin sheet which is positively charged. So it has a surface whose normal is pointed on this side and this face normal is pointed on this side. Okay. So now let us take sigma be the charge density on the sheet. Charge density on the sheet is sigma. So what is the flux coming out from both the surfaces? It will be twice of line integral of ds. So 2e ds cos 0. So total flux will be this. And ds, line integral of ds is ds only, because we are taking only this much area. We are taking only this much area. ds. 2e ds. But Gauss told the total flux coming out should be this. So now we will equal both. And E equal to this. This is the relation of the electric field due to infinite sheet. And now what is Q? Q is the charge per unit area. The area is ds. So the total charge is this. So ds cuts. It is sigma by 2 epsilon O. So remember, if the sheet is positively charged, electric field is outward, and if the shield is negatively charged, electric field is inwards. Please note them very, very carefully. Next, as you can watch here, electric field due to a thick infinitely charged sheet. So this is a thick sheet. Sigma is the charge per unit area. So due to the first sheet positive, electric field is outside, and due to the second sheet, electric field is also outside. So total electric field due to two thin sheets will be this. Please remember, this is for the thick sheet. Thick sheet. And this is the electric field due to a thin sheet. Please remember this. electric field due to two thin infinite parallel sheets. So watch here, we have taken two sheets, both positively charged. I want to find out what is the electric field in this part, and this part. So in the region 1, as you can see, due to this sheet the electric field will be out, and due to this sheet also electric field will be out. So we will add both the thin sheets electric field. Sigma 1 and sigma 2 are the charge per unit area. So this is the answer of this. Now in the region 2, for sheet A electric field is away, and for sheet B electric field is this. So net electric field will be subtraction of this. And in this region electric field due to sheet A is outside, electric field due to sheet B is also outside. So we will add it up again and we get this formula. So now if I compare that, if E3 is equal to minus of E1, if E3 dash is equal to minus of E1 dash, so sigma 1 equal to sigma minus of sigma 2. That means if you have charged the first sheet positive, you have to charge the second sheet negative. If this is charged positive, this sheet should be charged negative. So now friends, we'll be moving on to the numerical parts. So friend, let's get started with the numericals now, slowly. As we have covered up the chapter, theory part is now completed, and now let us move on to the numerical part. Okay, if 20 joules of work is done to move an electric charge 4 coulomb, this is Q, this is W, and I am moving from a potential 10 volt to another V volt. So what is the difference of the potential? The difference of the potential is V minus 10, because this is a higher potential. So V minus 10 is the difference of potential, is W by Q. So we can find out the V. Next, what is the work done in moving 2 microcoulomb from corner A to corner B when 10 microcoulomb charge exists at the center of the square? So see, here is a 10 microcoulomb. I want to move from here to here, this charge 2 microcoulomb. So what is the potential at A due to 10 microcoulomb? This is the formula, and it is 10 microcoulomb by 4 pi epsilon AO. This is the distance AO. Similarly, what is the potential due to 10 microcoulomb at B? It is the same. Okay, AO is equal to OB. So instead of OB, I can use AO. Now see, VA and VB are same, so their potential difference will be 0. So if the potential difference is 0, the work done to bring this 2 microcoulomb should be 0. Clear? Next sum, let us see. So next sum says, if a point charge plus Q is taken from A to C. So first I am taking the plus Q from A to C, and then from C to B of a circle with a charge. I want to take plus Q from A to C, C to B, and there is a plus Q charge at the center. So they are telling along which path the work done is more. So let's see from A to C. Okay, so potential difference is VA minus VC is this. Now please watch here. VA minus VC is, this is the potential difference. VA minus VC is VAB by Q. Similarly, from C to B, it should be VC minus VB WCB by Q. Okay. Now, from here, what we can see is that VA and VB potentials are same. Why? VA, what is the potential at A due to Q? It will be Q by 4 pi epsilon OR. And what is the potential at B due to Q? The distances are, it is Q by 4 pi epsilon OR. So that is why VA and VB are same. So this VB can be replaced by VA. So VC minus VA is this. So I can write it like this. Now VA minus VC is WAB by Q. Q cancels. So WAB is equal to minus WAB equal to WCB. So if I use the modulus, the work done by from A to B and from C to B is same. Work done from A to B and from C to B will be same. So VA, VC, we are going from A to B and from C to B, right? A to C and C to B are giving the same results. So that means it is the same work done. Next, calculate the potential at P due to a charge this located 9 centimeter away. So this is the charge which is 9 centimeter away. So I want to find out what is the potential at this point, and the formula is this. So Q 4 pi epsilon O this, and 1 by 4 pi epsilon. So we can easily find out this value. That is the volt. Okay, 9 centimeters written as 9 into 10 to the power minus 2. Clear? Next, potential at infinity will be 0. So if I bring a charge, this charge, if I bring from infinity to P, at P the potential is this, and at infinity potential is this. So what is the potential difference? This only, which is work done by charge. So work done by Q. 1 by 4 pi epsilon O is 9 into 10 to the power 9. Now, putting all the values, we find out that the work done is 8 into 10 to the power minus 5 joules. Does the work done depend on the path followed? Work done is a scalar quantity. It will not depend on the path followed. It depends only on the initial and final stages. It does not depend on the path followed. Clear? Next, infinite number of charges each Q. So see, this is x equal to 0. At x equal to 1, I have kept a charge Q. At x equal to 2, a charge Q. X equal to 4, a charge Q. X equal to 8, a charge Q. So this continues. So they are telling what is the potential due to all the charges at x equal to 0. At this point, what is the charge? So let's see, due to the charge at A, what is the potential at O? Q by 4 pi epsilon O R. R is 1. Due to the charge at B, what is the potential at O? The distance is 2. Due to the charge at C, what is the potential at O? Distance is 4. Due to the charge Q at D, what is the potential at O? The distance is 8. So if I add all of them up to infinity, I will see that Q by 4 pi epsilon O is common, and this is coming. Now this is a GP series. because this by this is giving half, this by this is giving half, this by this is giving half. So it's a GP series. And because it's a GP series and it's a sum to infinity, the formula, this is the first term of a GP series and this is the common ratio. Common ratio is half. So please note that sum to infinity of a GP series is this formula, A by 1 minus R. So A is the first term, which is 1, R is half, and calculating it we get this. So this is the net potential at O due to all the charges infinitely kept from x equal to O. Let's see the next sum. So there are two charges, this and this. They have shown you the charges at 15 centimeter apart, correct? At what point on the line joining the two charges electric potential is 0? At a distance x from here, the potential due to the charges is 0. So due to the positive charge, the potential at P will be this much volt, and due at P, due to the charge at A, this is the charge, the potential is this. Now for the potential 0, this should be equal to this, total potential should be 0. So on calculating and cancelling the common terms, we calculate x is coming 9. That means at a distance of 9 centimeter from O, the potential here due to the charge this and this will be 0. Next, there is a charge plus 1 microcoulomb held at O. This is the charge held at O. This is the charge held at O. 2 points A and B. A is 2 meter, B is 1 meter. Find the value of VA minus VB. Okay, so what is the potential at A due to the charge Q at O? Okay, this, and this R is given as 2 meter. What is the potential at B due to the charge at O? The distance is 1 meter. And it, what is then VA minus VB? Let us calculate. So this is coming this. Similarly, for the figure B, what is the potential at B due to the charge at Q? So it will be what? At Q, it will be what? Q by 4 pi epsilon O into 1. And at A it will be what? Q by 4 pi epsilon O into 2. Okay, so now VA minus VB. So it will come the same thing. It will come the same thing. Okay, if B and A are interchanged, so it is the same value coming. The same value coming. Okay, if B and A are interchanged, so this will not be affected. The value will not be affected. The value will not, the magnitude of the potential difference will not be affected. If B and A are interchanged, that means VA minus VB, the magnitude will remain the same. Clear? Next, the side of a square is given 0.1. This is the side of a square given. Find the potential at O. So see, potential at O. So potential due to A at O is this Q, I know, and the distance AO. AO distance, as you can see, we are calculating here. AO will be A by root 2. A by root 2. So here we have put. Similarly, due to B at O will be this. AO and BO are same. DO is same. OC is also same. Okay. So at C, due to C at O, the charge is given 10 to the power minus 6 and distance is this. Due to D at O, charge is given this. So the total potential at O, we will add all of them, and if I add all of them, we are seeing that each and everything cuts. That means total potential at O will be 0. Second part says if E is the midpoint of BC, that means this is the midpoint. So this is 0.5 meter, 0.5, this is 0.05 meter. What is the work done to carry a charge from electron from O to E? I want to carry an electron from O to E. What is the work done? Okay, so let's see. The potential at O is how much? 0. So find the potential at E due to all the charges. So due to charge A at E, this is the potential. AE, see the calculation AE, DE, the calculations, and also BE, the AE, DE calculations are shown here, which is coming 0.05 root 5. AE will be what? AB square plus BE square. So here I have shown 0. This will be 0.5. 0.05. Sorry. Okay. Similarly, DE, charge at D at charge due to D at E will be this. Charge due to B at E will be this, and charge due to C at E will be this. So what is the net potential at E? These will cut out. So net potential at E is coming 0. Potential at O is 0, potential at E is 0, so potential difference is coming 0. So definitely work done will be 0, because potential difference, work done is potential difference into Q. Let's see the next sum, friends. Find the potential at A and C. Okay, at A, potential will be due to both the charges. Charge due to the plus 2 microcoulomb charge and minus 5 microcoulomb charge. So at A, the potential will be due to D at A and due to B at A. So this is the due to the charge minus 5 microcoulomb at A. The distance is given to you 5 centimeter. So this is the distance. Formula is what? Formula due to a point charge potential, formula due to a point charge 4 pi epsilon O R. So Q I know this is the Q, R I know this is the R, and 1 by 4 pi epsilon O value I know. So putting all the values, we can calculate the total potential at A, which is coming this. Total potential at A. You'll see the calculations. Okay. Similarly, at C, the potential will be due to D at C and due to B at C. So this is the due to D at C, the distance is this, and due to B at C, the distance is this. So we calculate it, we get this. So now potential difference between A and C is this minus this. So which we get minus 42 by 5 into 10 to the power 5 volt. So what is the work done to carry the electron? The work done to carry a 3 microcoulomb, work done if I carry a 3 microcoulomb from A to C. This is the 3 microcoulomb I want to carry from A to C. So we know what is the potential here. We know what is the potential here. So we found the potential difference also, which is this. So work done is potential difference into the charge and potential difference. So this is the answer, 2.52 joules. Next, a small particle, this is the particle which is held between two plates. Okay, the charge is negative, so it will get attracted to the upper plate if it is positive. Then only it can remain suspended. It is at one place. That means the force of attraction on the charge due to the positive plate up and the weight acting down should be equal. Okay, so what is the potential difference that is given is 300 volt. So what is the force acting on the charge QE, which will balance the weight? E is V by D, we all know that. So putting all the values, we can find out the mass of the particle. An uniform electric field, this is E, exists in the vertical. So this is the uniform electric field. It is in the vertical direction. So if I move up, potential will increase, and if I move down, potential will decrease. Find the increase in the potential as one goes up to a height of 150. So we know that the direction of the electric field is in the direction of the decreasing potential. That is why minus is coming. So 10 volt, this I don't know, the distance is given. So this is the increasing potential. So if I go 150 centimeters up, I will face a potential of plus 15 volts. Next, two identical plane metallic plates. So see, these are the two metallic plates A and B. B is given earthed and the distance between them is given as 1 centimeter in air. Okay, A is given 10 volt and B is earthed, so VB will be 0 and VA is 10 volt. What is the magnitude and direction of the electric field? So see, the potential decreases, so that is the direction of the electric field. This is the direction of the electric field. Okay, magnitude of the electric field is given as this. So 0 and minus 10, distance given to us 10,000 volt per meter. What is the work done in moving 20 microcoulomb from X to Y? So X potential difference and Y potential difference will be the same because they are on the same plate. So potential difference between X and Y is 0. So work done to carry this charge will be 0 from X to Y. The kinetic energy of a particle decreases by 10 joules as it moves from a point 100 volt to 200 volt. Find the charge on the particle. So see, we know the increase in the potential is about 100 volt. Okay, and work done is given to us. So charge can be found. Next question is, two particles of masses 5 gram each and opposite charges, this and this. So these are two charges, both are 5 gram each, and charge of this is given as plus 4 into 10 to the power minus 5 coulomb, and this is given minus 4 into 10 to the power minus 5 coulomb. Okay, separated by 1 meter. Find the speeds of the particles when the separation is reduced to 50. So initially they were at rest, and now when they come close to a distance of half meter, they are telling what were the speeds of both of them. So definitely if they were moving together, their speeds would be same. That means V1 is equal to V2 is equal to V. Now the distance has reduced to half meter. It was 1 meter. So what was the initial potential energy between the two? This is the formula of the potential energy. This is the formula of potential energy in the final. Distance is half, which is this. So how much has that potential decreased? That is the increase in kinetic energy. So this is the potential final minus initial is the increase in the kinetic energy. So from here, V mass I know, so V square, and so V I can find 53.7 meter per second is the final velocity of the two particles. Find the electric potential energy of the system of charges. Okay, so see here, plus Q, minus Q, minus Q. So see, potential energy will be due to the combination of all the pairs between these two, these two, these two, these two, these two, and these two. So 6 pairs are there. So these are the 6 pairs which we are finding. So distance between A and B, A and D, A and B, as you can see, AB, the distance is taken as A. Charges are Q and Q. Between A and C, the distance is root 2A, and charges are Q and minus Q. A and D, the distance is A, and the charges are Q and minus 2. B and C, the charges are Q and Q, and distance is A. Between D and C, the charges are Q and minus Q, and the distance is A. Between B and D, charges are Q and minus Q, distance is root 2A. So we see that this is the final answer, and then on simplification we get this is the total potential energy of the system. Let's see the next sum, friends. So the next sum says, find the work done to put together this arrangement. That means I want this arrangement. What is the work to be done? Fine. Now, total work done to bring the 4 charges given. So see, here we will take 6 pairs, as you can see. Pair 1, pair 2, pair 3, pair 4, pair 5, and pair 6. The charges between A and B, the distance is known, A and B, it is D. Charges between A and C is Q, and distance is root 2D. This is root 2D. Similarly, this is also root 2D. Okay. So distance between B and C is D, and the charge is Q and minus Q. Distance between C and D is D, and charge is Q and minus Q. Distance between B and D is root 2D, and charges is Q and Q. So on simplification we get this is the total energy of the system. Now they are telling a charge Q0 is brought from center of the square, the 4 charges being held at the corners, how much extra work? Okay, so if I want to bring a charge Q0 to the center of the square, how much extra work I have to do? So please watch here that I have to find out what is the charge is being brought from infinity to this position. So what is the potential due to all the charges? First of all, here potential at infinity will be 0. What is the potential here due to all the charges? It will be 0 only. Potential due to A at E is what? Q by 4 pi epsilon O AE. B at E will be minus Q by 4 pi epsilon O BE. C at E will be Q by 4 pi epsilon O CE. D at E will be minus Q by 4 pi epsilon O DE. Now AE equal to BE equal to CE equal to DE. That means all these will cut out. So net potential at E is 0 and at infinity is 0. So potential difference 0. So no work will be done. No work will be done to bring an extra charge from infinity to the center of the square. Next, let's see another sum. Determine the electrostatic potential energy of a system of charges, this and this, placed at this and this. So let's see. This is the center. This is 9, 0, 0. This is minus 9, 0, 0. That means the distance between them is 18 centimeter. So the potential energy is, the formula is this, and this is your R. So here we are using this and we are getting, this is the potential energy of the two charges. How much work is required to separate the two charges infinitely away? Now if they have, the energy between them is this, so to separate them I have to give this much of extra energy outside, from outside I have to give them this much extra energy. If they have this much of energy between them stored, so I have to provide this much extra energy from outside to make them free. If the system of charges is placed in an external field, this is the external field relation. Value of A given. What would be the electrostatic energy of the configuration? So watch here. This is the external electric field. Electric field is this. Okay. So E equal to minus dV by dr. So dV equal to minus E dr. So this is what is the potential? E dr integration. So 1 by r, this is r squared to the power minus 2, which is this, which is this. Okay, so this was the original electrostatic energy between the two, and due to the external electric field, what is the extra energy? So please watch. This is this is your potential. So V into Q, this is your V into, this is the potential into Q. Similarly, V into the Q. Okay, there were two charges. So potential due to this charge 7 plus 7 microcoulomb and minus 2 microcoulomb. So this was our V, okay, and distance between them was, this is 9 centimeter and this is 9 centimeter. So what is the extra energy? This is the distance. This is here, in place of R I will put the distances of the two charges separately into Q. That will give me this was the original energy plus this energy also. So this is the total work done. Next, friends, let's see the next sum. The next sum says a charge Q is placed at the above the square plate at a distance of a by 2. What is the flux through this surface? So what we will do is that we will first complete a cube. So see, as you can see here, we will complete a cube. This is a by 2. So with another a by 2 as a side, that means each side is now a. I will complete a cube. And Gauss told that if there is a charge in a closed surface, the total flux coming out will be Q by epsilon O from all the 6 faces. So from any one face it will be by 6. From any one face it will be by 6. Clear? Next is we see here electric field in a region is given as this. This is the I component, means X component of the electric field, and this is the J component, means this is the Y component of the electric field, and E0's value is given to us. Find the flux of this field through a rectangular area. This is the area given parallel to YZ plane. Okay, so see, as you can see, this is the Y axis, Z axis, X axis, and our electric field components, X axis is like this, Y axis is like this. Okay, now this is a plane parallel to the YZ plane. That means this surface's normal will be like this, and electric field is also like this. That means the angle between them is 0 degree. So what is the flux through this part? Flux through this part will be Ex dA. Ex is 3 by 5 E0. dA cos theta. Theta is 0 degree. Area of the surface is given 2. E0 is given. So calculating we get this. Now through Y, electric field through Y and normal are 90 degree. That means electric field along the Y axis would be 0. Similarly, electric field along the Z axis will also be 0. So total electric field will be only along the total flux will be only along the X axis. Total flux will only be along the X axis, because in the X axis the normal is making 0 degree, along the Y axis the normal is making 90 degree. So we cannot have any flux along the Y axis, and along Z axis also the electric field does not exist at all. Next, the electric field components, this is the X axis electric field, and Y and Z axis components are 0. Alpha given. Consider this cube. Find the flux through the cube. Okay, so please watch. At this surface, the normal is like this, and at this surface the normal is like this, and electric field is moving like this. So there will be no flux from this surface or this surface, and sideways, only along the x-axis we will count. So total flux will be along the left side L and along the right side R, and flux is E dot ds. So for this part we will write Ex ds cos 180, because left side the normal and the electric field are at 180 degree for the left side, and for the right side the normal and the electric field are on the same side, so angle is 0 degree. So Ex is given as this. Clear? Because Ex's value is given alpha x. Here x will be taken as A, and here x will be taken electric field along the x-axis on this side and this side. Till here x is A, and till here x is 2A. So that's why here comes 2A ds. So now we are taking the common. Integration of ds will be the area, which is A square. Integration of ds will be the area A square. So on calculations we get this. So let us put the values as much as possible. A's value is known to us, alpha known to us. So this is the total flux coming out. So they told, now what is the charge inside? What charge is there? Gauss told total flux is Q by epsilon O. So Q equal to phi into epsilon O, and phi is known to us. Epsilon O is this value. So if I calculate it, I can get the total charge inside the cube. Let's see, friends, the next sum. An electric field, this is the x component given for x greater than 0. That means this is the x component of the electric field. This is the minus x component of the electric field. A right circular cylinder of length 20, this is the 20 centimeter length. Radius given 5 centimeters. Has its center at the origin. This is the center at the origin. This much is 10 centimeter, this much is 10 centimeters. What is the net outward flux through each face? So flat face. So see, this is one flat face and this is one flat face. Okay. So through this flat face, electric field is this, normal is this. So the angle will be 0 degree here. And through this face, so both the flat faces at the right and at the left. At the right it will be 0 degree between the normal and the electric vector, so it's cos 0. And on the left it will be the minus cos 180 degree, because normal is this side and electric field is on this side. So here we will take in the minus E, the value of E is given to us, and area of the circular plate, radius 5 centimeter, is pi into 5 into 10 to the power minus 2 square. So this is the area ds, this is the E part, this is the E, and on calculation we get this. Now they are telling what is the flux through the sides of the cylinder, that means surface. So I will write E ds. Now this is the normal and this is the electric field. So it is 90 degree, so no flux will come out from the curved surface. So total flux is how much? Only the flat surface. This is 0, which is this total flux. So what is the total charge inside it? Gauss told total flux is Q by epsilon O. So Q is this. So we can get the total charge which is inside the cylinder. Next, friends, let's see another sum. So this is a sum. A positively charged point nucleus ZE. This is ZE. Positive charge. Surrounded by a uniform negative charge. So these are all negative charges. All negative charges. Okay. Of radius R. The whole atom is neutral. That means total positive charge and total negative charge is 0. For this model, what is the electric field at a distance R from the nucleus? Okay. So I have to find out what is the electric field at this position from the nucleus, or at this position from the nucleus. It can be inside and it can be outside. So let's see. First we'll see if R is out of the sphere. So two charges are actually working here. One is the positive charge plus ZE. One is the negative charge minus ZE. It should be equal. The total charge inside the sphere is coming as 0. So there will be no net flux. Okay, if I consider electric field outside, no net flux. So if there is no net flux, that means the electric field at P will also be 0, because E equal to phi by A. If the flux is 0, then electric field at outside the atom will be at a distance of R. This is the R distance, will be 0. Next, I want to find out what is the electric field. What is the electric field at a distance of R? Here. So that means you can see here the full positive charge is taking place. So plus ZE. Okay. Now minus ZE is contained in the remaining of the volume 4 by total minus ZE is contained in 4 by 3 pi r cube volume. Okay. So in this much volume, how much negative charge is there? In the full 4 by 3 pi r cube, the negative charge is minus ZE. So only in this much volume, how much negative charge is there? So it is this much. So now we have got total charge. This is the plus charge and this is the minus charge. Okay. So this is the total charge of the thing up to a distance R. So phi will be Q by epsilon O. So this is the total charge by epsilon O. And electric field will be phi by area. Area is 4 pi r square. So dividing it, we get this. This is the electric field at a distance of R for a solid atom. Next, let's see, friends, another sum. At an altitude of 300 meters, so this is 300 meters, as you can see, at 300 meters, electric field is 60 volt per meter. And an altitude of 200 meters, here it is 60 volt per meter, and here it is 100 volt per meter. Okay. Find the net charge contained in a cube of 100 centimeter side located between the 200. So what is the net charge inside this? First of all, the potential difference we can find out here, as you can see here. Okay, so my question is, the electric potential decreases as we go up. That means electric field's direction. Electric potential decreases as we move opposite to the direction of the electric field. So electric field is directed downwards. Downwards. So due to this surface, what is the normal coming out? Like this. Electric field is also like this. So theta will be 0 degree. And for this, normal is coming out like this. Electric field is down, so theta will be 180 degrees. So this is the flux coming out through both the surfaces. Okay, cos 180 is minus. ds is 100 meter square, 100 meter square, because they have given that the cube is of side 100 meter. So this is the net flux coming out. And we know net flux is equal to Q by epsilon O by Gauss's theorem. So Q can be found out using this. Next sum, let's see friends, what is there? An electron is fired directly towards the center of a large metal plate. So here we are firing an electron towards the metal plate. And that has an excess negative charge with surface charge. Surface charge density of the plate is given. This is the sigma. If the initial kinetic energy of the electron is this, and it is, so here the kinetic energy becomes 0, and here the kinetic energy was 100 electron volt. Okay. And it will stop due to repulsion, because this is negative charge and this is also an electron. It will stop due to repulsion, so it will lose its all energy. So loss of energy. So see here, the electric field due to the plate is given as minus sigma by epsilon O, because it is negative charge. This is the surface charge density. Electric field I know. So what is the retarding force acting on the electron? EE, which is this retarding force. So what is the retardation on the electron? Force by mass. This is the mass of the electron. Okay, which is coming out to be this much meter per second square. Now final velocity is 0. Initial velocity, how can we find? It had initial kinetic energy 100 electron volt. 1 electron volt is 1.6. Please note that 1 electron volt is 1.6 into 10 to the power minus 19 joules. So this is the kinetic energy. So what was the initial velocity of the electron? This. Final velocity will be 0. Why? Because they are telling it will stop. So using v square u square 2as, we can find out the distance from which the electron should be fired. Next sum, friends, let's see the next sum. The next sum says that there are 3 charges 0.1 coulomb placed at an equilateral triangle, sides given 1 meter, 1 meter and 1 meter. They are telling that I am supplying energy at 1 kilowatt hour. That means 1000 joules per second. I am supplying energy at 1000 joules in 1 second. I am supplying. How many days would be required to move the charge A from here to D? Okay, so first of all I have to find out the potential here and the potential here due to the both the charges B and C. So let's find out the potential at A due to B and C. At A it will be due to B and C, 1 by 4 pi epsilon O. This is the Q by R, 1 meter, again Q by R. So this is the potential at A due to B and C. Potential at D due to B and C. Now here distance will be taken as half meter, 0.5 meter, and this is 0.5 meter. So potential due to this at D and due to this at D. Here we are finding it out, which is coming this. So what is the potential difference between A and D? We'll subtract both values. This value and this value we will subtract, taking commons. So this is the potential difference, and as you can see, if I put the value 1 by 4 pi epsilon O, this is the potential difference. So work done to move this charge (0.1 coulomb) through this potential difference is this much joules. Now we know that I am supplying in 1 second, I can supply 1000 joules. So I need this much of joules. So how much time would it require? This by 1000, this much second. Dividing by 3600 give me days, and dividing by 24 hours give me the number of days. Total this many days will be required to move the charge from A to D. So next, let us see the sum. Okay, so there is an electric dipole. As you can see that there is a dipole minus Q and plus Q separated by 2 millimeter. The negative charge is at a distance of 2 centimeter from a line charge. This is the line charge, infinite. Okay, and the linear charge density is given. Charge per unit length is given to us, lambda 4 into 10 to the power minus 4 coulomb per meter, lambda. Okay, so now we already know that electric field due to a line charge infinite wire is this. Lambda is given to us. We put the values. So electric field due to this wire at a distance of A, which is 2 centimeter, is given by this. Similarly, electric field, so it is minus Q. It is minus Q. So please watch carefully. That means electric field will be in this direction, and for the plus Q it will be in this direction. So at B electric field, the distance will be what? 2 plus 0.2 centimeter. That means 2.2 10 to the power minus 2. So what is the net electric field? We will subtract both. We're getting this. Now putting the value of lambda, this is lambda, 1 by 4 pi epsilon O is 9 into 10 to the power 9. Putting the values, we get this is the net electric field due to the dipole. Due to the long electric charge wire, a dipole will have how much electric field? This much. So what is the net force acting? It will be Q into electric field, Q into the electric field. This is the Newton. So this is the net force acting on the dipole. So friends, with this we have completed all the numerical portions of the potential, electric potential chapter. So I have covered up each and every portion of the potential chapter, including the theory and the concepts and the numericals, and I hope that if you follow them slowly along with me, if you keep following it, then you will be understanding. I have given you the complete knowledge of the chapter. So my request is, please go through the chapter notes, note down the notes on your own, do the numericals along with me, try and do the numericals with me so that you can be confident and how to face the numericals. Note down the formulas, derivations. I have shown each and every derivation which is going to come for your board examinations. So keeping this in mind, I have completed the full chapter, and my request is please go through each and every numericals and try and do them all on your own, and note down the list of formulas which I am highlighting. Okay, so with this we finish the full chapter of the potential, and I would again request you, please go through the other chapters of the electrostatics, the chapter 1, 2. First go through this, because then only you will understand this chapter 3, and after that we have chapter 4 of capacitance. So please go through these chapters, then only you will be having a link and you will be able to understand. So once again, thank you so much for watching Parijat sir classes, and I suppose you will definitely like, share and subscribe the channel for motivating me to make more and more videos like this. Okay, so till then it's goodbye from my side, and thank you so much.